Introduction to Work and Energy. Energy is defined as the ability to do work. Examples of work done are a person pulling a load on a surface, a locomotive engine pulling the carriages to a distance. To perform such work, the objects need to possess energy. Mechanical energy can be classified into potential energy and kinetic energy. Examples of objects having potential energy are an object at a height above the ground, a compressed spring. Examples of objects having kinetic energy are a running train, a bullet fired from a gun. A stone thrown into the air will possess both potential energy and kinetic energy. In this lesson, you will be able to understand the definition of work, learn the formula for work done, dW equals FdS, learn to use the force displacement graph, understand the definition of energy, learn to classify mechanical energy into kinetic and potential energy, classify potential energy into gravitational potential energy and elastic potential energy, learn to apply the formulae. Kinetic energy EK equals half mv squared. Change in gravitational potential energy delta U equals mgh, and elastic potential energy U equals half ke square. Click the play button and observe. The block is pulled by a force F on a smooth horizontal surface. As a result of the applied force, the block moves a displacement of S. Then, work is done by the force F. S is the displacement of the object.
Ladies and gentlemen, the displacement, you notice or not, we use a displacement. So that means distance moved by an object in a given direction from a fixed reference point. That means that they must be the direction. So here in this case, this force F must relate to the direction, where the force must be in the same direction of the displacement.
Work done by the force on an object is defined as the scalar product of the force F and the displacement S of the object. W equals F dot S, where F is the force applied, S is the displacement of the object. Draw a force displacement graph. Click the play button and observe the graph being plotted when a constant force F is applied to move any object from S1 to S2. Work done is the product of the applied force F and the displacement S and is given by the area under the graph between S1 and S2. Now, click the play button and observe a variable force applied on any object. Thus, for a varying force, the total work done can be calculated by summing up the work done by the force through a small displacement ds. For a small displacement ds, the force F may be assumed to be a constant. Work done for a small displacement ds equals dw, which equals F ds. When the displacement varies from S1 to S2, total work done by the force can be calculated as shown. W equals summation of f ds, which equals integration of f ds from limits S1 to S2, which equals area under the force displacement graph between S1 and S2. Click the play button and compare the movement of each of the blocks when the same force F acts at a different angle to the direction of displacement. Which block is displaced to a further distance in the same time interval? Displacement S2 of the block on the right is greater than the displacement S1 of the block on the left. This is because the force is inclined at a small angle to the direction of displacement. If the angle between the force and displacement is smaller, more work is done.
That means that if the force nearer to the horizontal, that means that the smaller difference of any angle, yeah, the smaller change of the angle from the force to the horizontal displacement, the direction of the object, that means that the greater will be the resultant force. So from here, that means that if this is the force F, that means the Fx will be greater because F cos delta, right? Cos smaller angle, that means it will be greater. Horizontal component will be greater. So that means that W equal to Fs. That means that the work done will be higher.
The force makes an angle theta with the direction of displacement of the object. As a result of this force, the object is displaced by a distance s.
So that means that F, when we resolve into the same direction of the movement, same direction of the displacement, that means that it will be F cos delta. This F will become F cos delta for the horizontal component. Vertical component will be F sin delta, where the relationship F sin delta will be equal to mg in the equilibrium position.
We know that work done is the scalar product of force and displacement. Therefore, W equals F dot S, which equals Fs cos theta. Consider a certain mass of gas in a cylinder fitted with a moving frictionless piston of cross-sectional area A. In the equilibrium position, the force exerted by the gas on the piston is calculated. Force exerted by the gas on the piston is given by F equals P times A, where P is the pressure of the gas and A is the cross-sectional area of frictionless piston.
So this formula comes from the pressure equal to force over cross-sectional area. Cross-sectional area, that means that the area of the cylinder, the area of the surface of the cylinder, cross-sectional area or area of the piston.
Click the play button to observe when the gas is being heated. The piston moves slowly with a small displacement dx.
Observe that when I click the play button, the heat is supplied to the gas. The gas absorbs heat and it will expand.
The work done by the gas can be calculated as dW equals F dx, which equals P A dx, which equals P dV, where dV is the change in volume, which is A dx. The total work done to increase the volume from V1 to V2 can be expressed as shown. Total work done, W, equals integration of dW, which equals integration of P dV from limits V1 to V2. Click the play button to observe the pressure volume graph being plotted. Click on P1 and P2. Observe that the volume of the gas increases from V1 to V2 as pressure decreases from P1 to P2. Work done by the gas is given by the area under the pressure volume graph. Summary. Work done by the force on a body is the scalar product of force and displacement of the body. Work done by a force can be calculated from the area under the force displacement graph. For a variable force, the total work done can be mathematically expressed as a definite integral of force with respect to displacement. For a force acting on a body at an angle theta to the direction of displacement, work done is given by W equals Fs cos theta. Work done by the gas when its volume changes from V1 to V2 is given by W equal integration of P dV from limits V1 to V2. Observe the locomotive engine doing work as it moves. The locomotive engine requires energy to do work. The energy possessed by the locomotive engine due to its motion is kinetic energy.
Ladies and gentlemen, let's refresh the terms of the work. Work done by a force is the scalar product of the force and the displacement. And the energy is the ability to do work. And last, kinetic energy is the energy processed by a body due to its motion. That means that when an object is moving, it possesses the kinetic energy.
The energy possessed by a body by virtue of its motion is known as kinetic energy. If the mass of the engine is m and it moves with a velocity v, then the kinetic energy is given by the formula Ek equals half mv squared. Let us consider a constant force F acting on an object of mass m on a smooth horizontal surface. If the displacement of the object from P to Q is s, then the work done W equals Fs. Since F equals ma and V squared equals U squared plus 2as, W equals Fs, which equals mas, which equals m times V squared minus U squared over 2, which equals half mv squared minus half mu squared, which is the change in kinetic energy. Thus, the change in kinetic energy equals the work done. Summary. The energy possessed by a body by virtue of its motion is known as kinetic energy. Kinetic energy equals half mv squared, where m is the mass of the body, v is the velocity of the body. Change in kinetic energy of a body equals work done on the body. Click the play button. An object possesses energy by virtue of its physical condition or due to its position. This energy is known as potential energy.
Ladies and gentlemen, the potential energy is the energy possessed by a body by virtue of its position or state. That means that the position means that the distance difference from the surface of the Earth. When an object drops down, the potential energy reduces.
As the ball falls down, its potential energy decreases as shown. There are two types of potential energy: gravitational potential energy and elastic potential energy. The weight possesses gravitational potential energy. The stretched spring possesses elastic potential energy.
Gravitational potential energy is the energy possessed by a body by virtue of its weight from the Earth's surface. That means that it's related to the gravitational force, gravity. Where elastic potential energy is the energy stored in a stretched spring or compressed spring.
Click the play button and observe. The person lifts the weight against gravity. The amount of work done to lift the weight against gravity is stored as the gravitational potential energy of the weight. Work done by the person is given as W equals Fs. If the person lifts the weight to a height h against gravity, S equals h, and the force applied by the person is given by F equals mg. Therefore, work done is given by W equals mgh. Work done in lifting the mass m through a height h increases the gravitational potential energy of the mass. Therefore, increase in gravitational potential energy delta U equals mgh. Observe the picture. The spring shown is neither stretched nor compressed, as there is no force applied on the spring. Click the play button and observe the spring. A person stretches the spring by applying a force. When the spring is extended by a length x, the force applied is given by F equals work done by force. A person stretches the spring by applying a force. When the spring is extended by a length x, the force applied is given by F equals kx.
F equal to kx, the k will be the force constant of a spring. That means the amount of force needed to extend or compress the spring for 1 meter or 1 cm, depends on the unit. If how many Newton per cm, that means that every compress or stretch of the spring of 1 cm need how much of the force. If that is how the force constant is in unit of Newton per meter, that means that the force needed to stretch or compress the spring for 1 meter.
Work done by force F is stored as elastic potential energy of the spring. Using the force extension graph for the spring, work done W equals integration of F dx from limits 0 to e, which equals integration of kx dx from limits 0 to e, which equals half ke squared, which equals half fe, which is the area under the force extension graph. Summary. Potential energy is the energy stored by a body by virtue of its physical condition or due to its position. There are two types of potential energy: gravitational potential energy and elastic potential energy. Change in gravitational potential energy delta U equals mgh. Elastic potential energy of a stretched spring equals half Ke squared.
Ladies and gentlemen, the summary of today's lesson are: okay, first, the work done by the force of an body is the scalar product of the force and the displacement of the body. Next, work by a force can be calculated from the area under the force displacement graph. Okay, Sing Eng sedang masuk. Okay, for a variable force, the total work done can be mathematically expressed as a defined integration of a force on displacement. For an inclined force acting on a body at an angle delta to the horizontal, work done is given by W equal to F cos delta mass. That means that the force must be in the direction, same direction to the displacement. And work done by the gas is given by W equal to the integration P change of the volume times with change of the volume with the limit from V1 to V2. Ladies and gentlemen, this is the exercise for today's lesson. So for the work and energy, we have question 1, question 2, question 3, question 4, question 5, 5 questions only for today's exercise. So ladies and gentlemen, later I wish you all do the exercise first and we discuss again on next lesson. So ladies and gentlemen, that is for the today's lesson, and I will stop the lesson here and we continue again tomorrow.